We're going to start the last section of the unit. Now, this section isn't like one simple, short little topic. It's a few little topics within the section, but they all kind of go together. A little bit of a change of gears from what we've been doing. We're going to start talking about energy today. Does anybody remember from last year in Science 10 or maybe some other year you've done science what energy means? There's a simple, short, quick definition for energy that I guarantee you've learned. It's just a matter of bringing it back to your memory. I have energy right now as I'm walking around the room. You have energy as well as you sit in your desk, although we each have a different kind of energy. Okay, I have an energy that's doing something right now. You have an energy that has, well, the potential to do something. Energy we define quite simply as the ability to do work, not necessarily doing work, although that's what I'm doing as I'm walking around the room, doing work. You're sitting at your desk, with the exception of those of you who have just decided to write something down. You are not doing work right now. You are not moving, but you do have the ability to do work because there's energy stored inside your body that gives you that ability. I'm doing work because I'm moving. You have the ability to do work. You have the ability to start moving. So we both have energy. We just have two different kinds of energy. What are those two main categories of energy? Keeping in mind that there's subcategories of both. But the two main categories of energy, one relating to motion, one relating to something else? Good. Kinetic energy and potential energy. So we're going to say that energy is the ability to do work, and the two types are kinetic and potential energy. Kinetic energy is the energy of motion. That's what I possess right now because I'm doing work. You have stored energy or potential energy, not because you're doing work, but because you have the potential to do work. Okay? My car sitting in the parking lot isn't doing any work right now, but it has the potential to do work because there's energy stored in the gasoline in the tank of my car. When we are moving or causing something to move, that's actually doing it now. That's kinetic energy, doing work now. When we just have the potential to make something move, the potential to change to kinetic energy, that's potential energy. That's stored energy. Now, we learned an equation way back in in Science 10 for kinetic energy. Does anybody remember what it is? Probably? No? Okay. Do you remember it, though? Yeah, you can figure that out, right?
Is it mv, or 1 over 2 mass v squared?
Yeah, good. EK is equal to 1/2 mv squared. Kinetic energy is 1/2 of mass times, what does V stand for?
Velocity?
No, but you're close. M is mass, measured in kilograms. V is, it's not velocity, but it's close. Speed, measured in meters per second. It's important. We're not squaring the velocity because the direction here doesn't matter. We're squaring the speed. EK stands for kinetic energy, of course. What would the units for kinetic energy be? Anybody remember this from Science 10? Yeah, joules. And what would it be, a vector or a scalar? It's a scalar. So in other words, if I have 1,000 joules of kinetic energy, it doesn't matter whether I'm moving to the right or left. That's how much kinetic energy I have. It's not a negative because it's to the left and a positive because it's to the right. Kinetic energy is a scalar. In fact, all types of energy are scalars, including kinetic, and all types of potential energy and change in energy and so on are all scalars. We're going to do some questions with kinetic energy in just a couple minutes. But first, let's take a look at potential energy, the stored energy. We usually break this down into some categories, subcategories. What would one type of potential be? After you answer my question, yeah. Yeah, one type of stored energy. What's something that gives something, not something that's doing work right now, because that's kinetic energy, but something that gives something the ability to do work. A spring, okay, good. A spring, or sometimes we combine that with elastic potential energy. When a spring or an elastic is stretched or squished or compressed, right, then it has the ability to do work. When I stretch an elastic and let it go, what happens? It flies across the room, right? So it has the ability to start moving across the room. It has the ability to do work. So it must be stored energy. What else we got besides the elastic or spring potential energy? What else can make something start moving? We talked about one of them already. Yeah. Okay, that's not the one we were talking about, but that can. Right? This pen is in my hand right now. It's not moving. It's not doing work, but has the ability to do work, right? All I got to do is take away my hand, and the pen starts falling. So there must be something caused by gravity that gives the pen the ability to do work. And there is. We call it gravitational potential energy. That's the one we're really going to focus on in this unit. We'll talk about elastic and spring potential as well, and we'll come up with an equation that describes that. But the one that we really focus on is gravitational potential energy. Another one? The one we talked about earlier. My car sitting in the parking lot right now isn't moving. Has the ability to move, has the ability to do work. What kind of energy is stored in the car? Yeah.
Is it mechanical?
No, mechanical is actually, mechanical energy is the sum of kinetic and potential. So, and what you're going to learn later on in the unit is that mechanical energy remains the same. If you add up the kinetic and the potential, it remains the same. So in other words, as I stretch that elastic, okay, with a little clothespin spring in the inside, on the end of it, as I stretch that, has a certain amount of potential energy. As that potential energy decreases after I release it, the kinetic energy increases, so that the total energy or the total mechanical energy will remain the same. Your car has mechanical energy, sure it does. But specifically, what's the potential energy that makes up the mechanical energy? Where does it get its energy from? Don't tell me what kind it is, just tell me where it gets it from. In most cases, I think in all cases in our parking lot, it gets it from gasoline, right? What kind of energy is that? The energy stored in a chemical, just the same as in our body, right? Just a different chemical. Chemical potential energy. Now, we're not going to do too much with chemical potential energy this year, but I want you to know that that is a type of stored energy. Your car, your body, gives your car, your body the ability to do work. What other kind of car are we going to start seeing in the parking lot here in the next few years? I don't think we have any out there right now, but it's going to happen. Sometime before I retire, we're going to start seeing probably electric cars, right? Electric potential energy. We're going to talk about electric potential energy quite a bit in Physics 30, but not in Physics 20. Nuclear energy, that's the energy stored in the nucleus of an atom. It's not doing anything while it's there, but when it gets released, it can generate a lot of heat. And heat is really just kinetic energy, right? Because heat is the movement of particles, the vibration of particles. So you can cause kinetic energy from nuclear energy, so it must be a form of stored energy. Even solar energy, you could argue, is stored energy because it's not doing anything, but it has the ability to generate heat. It has the ability to generate electricity. It has the ability to do work. Okay, I want to focus right now for most of today on kinetic energy, and then we'll come back to specifically gravitational potential energy tomorrow. Kinetic energy is the energy of motion. We've established that it's equal to 1/2 mv squared. I want to do a problem that's on page 303. All of a sudden we're on chapter 6, jumping around a lot in this unit, eh? And the question says on a highway, a car of mass 1,200 kilograms traveling at 20 meters per second has a kinetic energy equal to a loaded van at mass 4,800 kilograms. Heavier van, right? What's the speed of the van? Would we expect, if the kinetic energy of this car is the same as of this van, would we expect the speed of the van to be more or less than the speed of the car? Would it? On what? Okay. Okay. Braden said it would depend upon if it was on a hill. We have to assume that it was not on a hill here. And the reason we have to assume that it's not on a hill is because it doesn't mention anything about gravitational potential. This is purely a kinetic energy question. Like, we're not saying like what's going to happen with potential energy that has the ability to make it move. We're saying, like, what's the situation while it's moving? What's the situation when it has kinetic energy equal to the kinetic energy of the car? If you have the same kinetic energy, the object with more mass will have less kinetic energy, won't it? Here's what I want to do. I want to do exactly what they tell me. There's a key word in here where they tell me exactly what to do. What is it? One word. And it's not speed. Okay, speed is like that's tunnel vision. Okay, if you're saying speed, you got tunnel vision. You're looking at this saying, oh, I got to find the speed. Yeah, okay, but like what's really going on here? Yep.
Find the kinetic energy of the car.
Yeah, okay, we are going to do that, but still just one word that's guiding me here. Equal, right? They're telling me here that the kinetic energy of the car, so Matty, you're right, we're going to have to find the kinetic energy of the car, but like the overriding principle here is that the kinetic energy of the car is equal to the kinetic energy of the van. And Megan, how do we know that? Because, yeah, they tell us. They tell us they're equal. So just do what they say. It's like your parents when they say, do what I say. And then you don't. But here, do what they say. Kinetic energy of the car is 1/2 mv squared. The van is 1/2 mv squared as well. There is a way to simplify this a little bit. Everybody see what it is? Just a short simplification. Not much, but a little bit, Kyle? Yeah, I can actually cancel with the half here, right? Because it appears in both terms. If you don't do that, like, oh well, like it's still going to work out. But if we do it, it saves us a little bit of bother. The mass of the car is 1,200 kilograms. The speed of the car is 20 meters per second. The mass of the van is 4,800 kilograms. Again, what do we expect to see for the velocity, the speed of the car? Or the speed of the van, I should say? Should be less, right? Bigger mass, less speed. 1,200 times 20 squared, what is that? I don't know. So let's figure it out. What do I get there? 480,000? Equals 4,800 times speed of the van squared. Let's divide that by 4,800. Equals 100. Let's square root that. 10. Speed of the van is 10. Yeah, you know what? It's less. Hey, it's less. But it's not that much less, actually. The mass is 4 times as much, but the speed is only half as much. Did some of you expect the speed to go down by a factor of 4? I don't know. I kind of expected it to go down a little bit more, right? How come it didn't? How come, even though the mass went up by a factor of 4, the speed didn't go down by a factor of 4? Yeah.
Is the mass and speed aren't like equivalent force?
Yeah. They're not linear. It's not a linear relationship. It's v squared. If it's v squared, then what matters more? Speed, right? Speed matters more. So what we find here is that just a small decrease in speed ends up having a fairly big effect on kinetic energy, a bigger effect than mass. We have to change the mass by more than we do the speed because speed has a greater effect. So our answer is 10 meters per second. Start off with kind of a hard one, eh? Okay, you're going to see questions in a moment here that are just, here's the speed, here's the mass, what's the kinetic energy? Easier than what you see here. Okay, good one to start off with. Because if you can do this one, you should be able to do the practice questions. All right, take a look at these 3 questions, please, on page 303. I want to have a look at number 3 up here. It says a skateboarder with a mass of 65 kilograms increases his speed from 1.75 to 4.2 as he rolls down a ramp. What's the increase in his kinetic energy? Now, by the way, as he rolls down the ramp, he increases his kinetic energy, right? Where does he get that kinetic energy from? Like you can't make energy. You can't just create energy from nothing. So it must come from something. What does it come from, Jen? Yeah, it comes from gravitational potential energy. You're losing gravitational potential as you go down the hill, and you're gaining kinetic, right? Potential has the ability to do work, has the ability to become kinetic, and that's exactly what's happening as it goes down the hill. The potential is converted to kinetic. All right, so we want to find the increase in kinetic energy, or in other words, the change in kinetic energy. Now, here's what some people want to do with this. I saw a few people trying to do this, and this is not abnormal. I see this all the time when I give this question. Some people say, well, wouldn't it be easier if I just said the change in speed is 4.2 minus 1.75, which is going to give me 2.45, is that right? If I subtract those two? 2 point what? 2.55? And then we say, well, EK is equal to 1/2 of mv squared, which is 1/2 of 65 times 2.55 squared. What's the problem with that? What's the problem, Jen? No, the rate of acceleration isn't actually increasing. Like if it's accelerating at 2.0, it's going to stay accelerating at 2.0, right? You just can't do that, yeah. Anybody else kind of help her out a little bit on that? Why can I not just say 1/2 of 65 times 2.55 squared?
It asks what the increase in kinetic energy is, so you have to know the 2 different kinetic energies.
Yeah. Yeah, like look, what are you trying to find? The change in kinetic energy. So you have to subtract the final minus the initial kinetic energy. Don't subtract the speeds.
The speed and kinetic energy is not linear.
Yeah, it's good, good. If, like, generally what we want to do is say just EK final minus EK initial, which is 1/2 mvf squared minus 1/2 mvi squared. Like generally, if we're looking for the change in EK, then we want to subtract final minus initial EK. You could actually get away with subtracting these 2 numbers and then subbing it in if it was a linear relationship between EK and V, which it's not. EK is equal to 1/2 mv squared, not 1/2 m times V. So if you're confused by that at all, just do it separate. Final kinetic energy minus the initial kinetic energy. Look, bottom line is, you can't do this because the equation is not 1/2 m times delta V squared. It's 1/2 mv squared, not 1/2 m delta V squared. So let's just do it from scratch. Let's say 1/2 of the mass of 65 times 4.2 squared minus 1/2 of 65 times 1.75 squared. Can I cancel with the 65s? No, because it doesn't appear in every term. Every term on the right side, but not on the left side. When we do the math here, it works out to be 474 joules. Okay, how many people ended up getting 474 in the end? Do you understand why we have to subtract kinetic energies as opposed to speeds and then kinetic energies? All right. Here's what I'd like you to do now. I'm going to give you a worksheet that has some questions on kinetic energy, and I would like you on that worksheet to do the first 7 questions in class here.